This will be effective offset on the signals coming from this thing, whatever it is. We were using this circuit diagram. But now we're using this circuit diagram. Because this is the one that is claimed to be the one that generated the traces that are used to support Rosemary's claim of battery charging or load heating without any depletion of the battery's charge. Okay. So I've rewired Tar Baby to reflect this circuit. It's pretty easy. All I had to do was take the MOSFETs out of the sockets and turn them around to make this circuit into this circuit. Okay, so here's your Q2 array of 4. Oh, and that's the beer I'm drinking right there. It's pretty good stuff if you like pale ales. Anyhow, there's my Q1. No, this is, who knows? This is that one, the Q2 times 4. You'll notice that its gate is connected to the positive terminal of the function generator. Okay? So Q2 4. There's the RFPG50 front of the MOSFET. Gate is pin 1. It's the small red wire, or the small wire on all of these 4 MOSFETs, and they go all the way over there to this side. This side, small wires to this side of the MOSFET bus, and if we turn it over, we see that that side of the MOSFET bus is connected to, whoops, sorry, I don't have a lot of hands here. That side of the MOSFET bus is connected to there, which is connected to the positive terminal of the gate of the function generator drive. Okay, so that should confirm that we're wired in this manner. All right. The other MOSFET is turned around with respect to that. You can see it's on the same bus, but you can see I got its socket turned around so that the gate is over where the source bus is for these MOSFETs. And here's it right here. This is the Q1 MOSFET. And you can see that I got it plugged in correctly here to gate to the source of the other 4. Right? Gate. Oh, sorry. Gate to the source of the other 4. All right. So normally I look at the transistor side of the load to view the common MOSFET drains right here, where all of the common MOSFETs drain into the load. Okay, so that's what's going to be on my B trace right here. I can also use that trace, or I could use the A trace to monitor either the current viewing shunt or the battery voltage, but usually I use it to monitor the function generator because that's the most relevant input and the gate drain is the most relevant output. Okay, so there's my 0 markers on the venerable old HP180A dual beam oscilloscope. Where does it say that? Oh, there it is. Yeah. See there? Okay. This oscilloscope was given to me by a scientist who actually used it at Lawrence Livermore National Laboratories on atomic weapons research. So it has a venerable history and it still works quite well. And it has features that you don't normally see on a lot of oscilloscopes. This time base actually is a dual delayed trigger time base, so I can display 2 different time bases on the same screen at the same time, which is kind of neat because I can actually go into those oscillations while they're happening and show their frequency and waveform at the same time I'm showing the much slower frequency and waveform of the function generator pulse and the circuit's response. Okay, but in this video, all I want to do is show the interstate high voltage function generator F43, how its offset control affects the signal that you get from the Tar Baby circuit. Okay, so I guess we're ready to go. Oh yeah, I've got this load on there. Could be using the other load just as well, but this one is more convenient for me because it's all sealed up. The other one is all just kind of out in the open and hangs there. This is a 10.3 ohm stack of wire wound ceramic resistors in parallel. Total ohmage is 10.3 ohms, and the total wattage handling capability is 60 watts. But since they're immersed in 250 milliliters of mineral oil, they should be able to handle considerably more wattage than that if required. I also have a little analog thermometer on there. I found that the RF emitted by the circuit just overrode my cheapo digital thermometers and made them go crazy. Okay, so anyway, so I got the channels off, and I've got the zero lines marked. Okay, there's the zero line for A, and there's the zero line for B. And I'm going to point the light away a little bit to make the trace show up a little bit more. Okay, so now what I'm going to do is just first we'll just turn the channels on. Click and click. So here you see a little bit of oscillation from the function generator already. And here you see the battery voltage. We're at 20 volts per division, 10x attenuated probe, and 5 volts per division for the function generator trace. Okay, so at 20 volts per division, we have 20, and then each little tick mark in there, since there are 5 tick marks in there, each one of those is going to be 4 volts. So we have 20, 4, 28, 32, 36, 37, almost 38 volts on there. And that agrees with what we've got here pretty well. Okay? And so that's the common, excuse me, the common drain trace. The fact that it's high means that the MOSFETs are off. The load is not seeing any current. Alright? So now I will turn up the amplitude of the function generator. You'll note that the function generator is set to produce a strictly negative going pulse, and we're at 2 kilohertz. Okay, and here's the offset control, or I'm sorry, here's offset, and it's pushed in, which means off. So I'm going to turn up the amplitude. Notice that it's all going negative. Okay. Boing. And there's our oscillations on the drain trace. And the more amplitude I give the function generator, the bigger those oscillations get. But let's just use a good, what do we got here? We're 5 volts, so we're going to give it about 7 volts or so. 6 or 7 volts. That's enough to turn the MOSFET on if it were actually seeing anything. Okay. You can see that the battery voltage has not, or rather the common drain voltage has not gone low at any point. So that means that no MOSFETs are really turning on here. MOSFETs are oscillating during the low portion of the trace. Okay. So now if I vary the offset, I'll pull the offset knob, and it was actually not set right at 0. If I set it right at 0 when I pull the knob, I shouldn't see any change, right? So there we're set right at 0. I'm pulling and popping the knob. So now I'll pull the knob and I'll start moving this, I'll start offsetting this trace by just moving it up. Okay? So up, 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 up. Right? Here we're back to where we were. Now we're going up. Those oscillations cease. Now we're showing about 3 volts plus or minus, and that's not enough to turn a MOSFET on. So now we continue going up, and as we get more and more positive, we see a MOSFET start, or rather some MOSFETs starting to turn on. Okay, see there? Now I'm going back down, up, 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 up. So with a positive going pulse, this is the kind of thing that we should be seeing. We should be seeing gate drive going to, or rather the drain signal going down to near zero, that indicates that the MOSFET is turned on in that stage. Now it's turned off, now it's turned on. And that's what you expect, because here we're 0 plus 5 or 6 volts, 0. So in that plus area, the drain trace drops because the MOSFET's turning on, right? If I go way up high to the point where the signal is completely above 5 volts, look what happens. The other MOSFETs start turning on. If I give it even more amplitude, there, look, all the MOSFETs are on now. See there, this is the drain trace, it stays low all the way across, so the MOSFETs are on. Look at that. Got 3 amps of current flowing through there. So if I go back to where just the one set of MOSFETs is on, much more reasonable current. And now if I crank that offset back down to where we get the oscillations, all negative going pulses, there, turn the amplitude down a little bit, and then all negative going pulses, don't have a lot of current flowing, alright? But just this fiddling around has raised the temperature of my load by about 10 degrees. It was around 80 when we started, I think. Even though, right now, we've got oscillation and no MOSFETs really turning on. Alright? So hopefully that clarifies the issue of what the offset control does to this circuit. Way up, ooh, way down, ooh. Look at that. By going way negative, I can get oscillations in both phases, and in fact I can just go like that, and that's turning the MOSFETs partially on when it's doing that. But both phases are oscillating nicely when you do this. See there? One phase is oscillating, no MOSFETs oscillating, MOSFETs turning on hard, one set of them, all MOSFETs turning on hard. And that's just from varying the offset. Alright? Okay. Thanks for watching. Oh, wait, before we close, maybe you don't like the fact that I'm looking at the common drains. So let's just unhook the drain. Alright. From where it was. And let's hook it to the battery directly. Let's see. Right to there. And then to the negative over here. Right to there. Alright. So now we're directly on the battery with that B trace. And you can see again the battery voltage. Now when I turn up the amplitude, there you see the characteristic oscillations sitting on top of the battery trace, right? Now, notice that we're up there at battery voltage when that happens. Well, if I go to AC coupling on that thing, like that, boom, now we're back down. Now we're just looking at the relative amplitude between here and here. The scope is ignoring the DC offset because we've selected AC coupling. So now I can go to a higher amplitude setting. Okay, and now I can vary the offset. And there's monster oscillations on the battery, you think. There's MOSFETs turning on hard. There's battery oscillations. There's everything oscillating. Okay. Now, I guess the moral of this story is that if you just show your device at one setting and you don't vary things, you don't learn very much. And if you measure the wrong things the wrong way, you also don't learn very much. Okay? Thanks for watching.